All right. Hello, everyone. Today we are going to do our last lesson for Unit 1 functions, which is inverses. So this is our last main concept that we have to get through in this Unit 1 functions, right? So inverses, every type of function is going to have some form of inverse. And we're going to go over how you find those inverses and why inverses are kind of important and things like that. Also, I'm very bundled up. It is freezing in my house today, and I refuse to turn the heat on because it's not time yet. I don't know. I don't feel like it's cold enough. Anyways, I'm freezing, so don't judge me for being like cardigan scarfed in my own house. I don't want to turn the heat on. Okay. Anyways, here we go. Okay, so first off, what is an inverse function? So you guys learned about inverse functions last year. Ooh, oh, my chair is stuck. Okay, last year in Algebra 2, you did, I believe it was when you guys were working with the exponential logs unit that you guys talked about inverses. But exponentials and logs, whereas they are inverses of each other, which is probably why you talk about them in that unit, but they're not the only function that has inverses. Like I said earlier, all functions have some type of inverse function. So we're going to talk about what exactly is an inverse function and how do you find it. So first off, an inverse function is basically the undoing of some function. All right, so that's kind of my definition I like to give. All right, so it's like the undoing of some function. Now, last year in Algebra 2, I believe you were taught two different ways. I think some teachers preferred one method over the other method. So one method that you guys learned was you were given like a function and you had to like write out the steps starting with closest to x, like what was happening, like we were adding 2 and then we were dividing by 4 and then like work your way out. And then to make the inverse, you just kind of went backwards and did the opposite. That's fine when you're first being introduced to functions, that will work. But that technique does not work for every situation. Most importantly, it doesn't work when you have an equation with multiple x's, which we have a lot. So even like a basic quadratic function, right? You have x squared, ax squared plus bx plus c, so you have two x's. Well, if you're trying to do the method where you write out what happens to x, we have two x's, so how do you know what to write out? Unless you put the function into vertex form, which nobody really wants to do. So there is a different technique, and that is to swap the x's and the y's in your equation and then get y by itself. And that's the technique that we're going to use in this class because that strategy works for every single type of function. All right, so we have the only method I'm going to go over. I'm not going to do that other one because it's not useful. All right, so to find the equation, so to find the inverse equation, I didn't even spell the rest of the whole word equation. I totally thought I spelled it. Oh man. It's Sunday night, y'all. Just cut me some slack here. To find inverse equation, we'll do a little arrow because why not? All right. You're going to swap x's and y's, then get y by itself. Okay, so you have your equation, y equals whatever. You're just going to, everywhere you have a y, replace it with an x. Everywhere you have an x, replace it with a y. And then you're just going to try and see if you can get your y by itself. That's it. So it's just a lot of algebra. This is something that's really good for practicing some of those algebra skills, which after grading some of the quizzes, we may need to do a lot more algebra skill practice because our order of operations is not exactly on point. Just saying, not calling anyone out, but I did notice. Some of us need to work on our order of operations. And this, practicing with inverses, is a really good way to practice those order of operations. All right, so now inverses graphically. So they are kind of interesting when you look at their graphs. So graphically. All right. Now, if you have a function and it's inverse both graphed, what it's going to look like is a reflection over the line y equals x. All right, so the inverse is a reflection of the original function over the line y equals x. And that's that diagonal line that goes like straight through 0, 0, and then like has the slope of 1. So it's like 0 and then like 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. That's that line y equals x. It goes negative 2. So you have like -1, -1, -2, -2 as like all your points on the line. All right. So it's a reflection. Well, sometimes it's a little bit hard for people to kind of see what's happening. So there is a way to, if you have the coordinate points, to figure out if you have like what the inverses points are going to be. And that is, you just switch the x and y's, which is basically what we do to find our equation. All right. So if you have the point, the coordinates, have switched x and y values. So for example, let's say f of x had the point -3, 7. The inverse function, now this is the symbol for inverse. So you have an f, and then we call this prime, f prime of x, or f, sorry, we put a -1. Ooh, hold on, let me just rewrite that. Boop, boop, boop. Forgot the -1. So f -1 of x, right? This is the symbol for inverse. Inverse symbol. All right. And if your function wasn't f, say your function was g, say you had g of x, then it would be g to the -1 exponent of x. So the -1 piece is like the symbol for the inverse. All right, so like I said, if f of x had the points -3, 7, then f inverse of x would have the point 7, -3. So you don't do anything to the numbers, you just switch the position, right? So this was x comma y. Now we just switched them, right? We just flipped our x's and our y. We didn't change anything about the values. We didn't do anything funky. You just trade positions. So like I said, if you do have a graph, you can easily figure out if two graphs are inverses of each other by kind of isolating some points on the graph and just flipping their x and y's and seeing where they land. That is inverses. All right, so now we're going to talk about something called one-to-one. All right, so there are not that many functions that are what we can consider to be one-to-one functions. They're actually special types of functions. So a function that is one-to-one means that the original equation and the inverse equation are both functions. Okay, so one-to-one means that, hold on, we'll do a different color here because we're about to run into the bloop, bloop, run into each other right there. All right, so one-to-one, an equation and its inverse are both functions. All right, so you have one equation, you have its inverse equation. If they are both functions, then we would say that this function is one-to-one. And what it means, one-to-one, is that for every one x, you have only one y. All right, well, that makes it a function, right? But it also goes the other way. For every one y, you have only one x. All right, so a quadratic equation is not one-to-one, right? Because for every one x, we sometimes have two y's, right? We have two y values. That's how we get that nice parabola shape, right? So we have different x values, but some x's have the same y's, like -1 and +1 have the same y value. That function is not one-to-one because for every y, there's not just one x. All right, so it has to go forwards and backwards. Graphically, it's very easy to figure out if a function is one-to-one because it will pass the vertical line test, which we know tells us if something is a function. It will also pass a horizontal line test. All right, so the equation when graphed will pass both a horizontal and vertical line test. Okay. Now, why are one-to-one functions important? Why do we care? Well, sometimes when we make that inverse equation, you want to see if certain things are going to happen. Like, does it apply with the other function rules? Like, so when you do quadratics, if you do its inverse, right? Well, we know there are certain things that happen with functions, right? They have the transformation properties. They have composition properties. Well, if something's not a function, doesn't mean it's going to follow along with those different properties that we've learned. Those are specific to functions. So if you have an inverse equation that's not a function, it's not necessarily going to follow any of those rules that we've kind of been learning throughout this unit. But yeah, so it's just something kind of to look at. So that's what one-to-one means. It means the equation and its inverse are both functions. Graphically, it will pass a horizontal and a vertical line test. So let's practice making an inverse equation. All right, so this one's going to be a little bit harder than what some of you guys are probably used to from Algebra 2 because we do have two x's. All right, and you guys didn't have to make any inverse equations when you had multiple x's. So this is the first time, and these are a bit challenging. Like I said, it does require a lot of algebra work, right? Order of operations, things like that. So here we go. All right, so the first thing that we're going to do, if we want to find the inverse equation for f of x, we need to first switch our x and y's. All right, so we know that f of x represents y in the equation, right? So this is really y equals x plus 2 over x minus 6. Okay, so first thing we're going to do is, like I said, we're going to swap our x and y's. So this becomes x equals y plus 2 over y minus 6. Okay, now there are definitely a couple techniques. I've seen students do this a few different ways. My recommendation and how I'm going to solve it is I don't like working with fractions. So the first thing that I'm going to do probably every time I'm working with problems like this is to get rid of the fraction, which means I'm going to multiply both sides of my equation by y minus 6. Because then the fraction part's going to go away and I will be left with x times y minus 6 equals y plus 2. Okay, so let me move my head a little bit. Boop, boop, boop. There we go. Now my head's moved. All right, so next, what we're going to do is, and again, there are a couple different techniques, but what I'm going to do is I'm going to distribute the x into that parentheses. That's going to give me x times y minus 6x equals y plus 2. Right, now that might seem like it made things really more challenging than it did, but in a second you're going to see why I did it. So I'm going to move everything that has a y in it to the left-hand side and anything that doesn't have a y in it to the right-hand side. All right, so I want to get all the things with y's in it on the same side of the equation. So I'm going to subtract y on both sides. And I'm also going to add the 6x because I want to get things that don't have y's away. So I added the 6x, so that's going to move to the right. And then I'm subtracting the y, so it's going to move. So now I'm left with xy minus y equals 6x plus 2. Now, again, this is where a lot of people get stuck, all right? But think about the algebra techniques that we've worked on. Number one, factoring. What do you notice about both terms on the left-hand side? I hope you said they both have y's in them, because they do, which means we can factor out that y value. So I'm going to GCF out that y, and what I'm left with is x minus 1. Now, remember, I want to get y by itself, so I just divide the stuff that's being multiplied to y away, move it to the other side, and I will have y by itself. So I'm going to divide both sides. All right, we'll keep moving sideways, like running out of space because I have that really cool banana picture we're going to talk about in a second. All right, so hold on, I'm just going to rewrite this. X minus 1 equals 6x plus 2. And like I said, I want to get y by itself, so I'm going to divide by x minus 1 on both sides. Those cancel. So now I'm left with y equals 6x plus 2 over x minus 1. And guess what? That's it. So f inverse of x, this equation over here that I was trying to find, is 6x plus 2 all over x minus 1. That is my inverse equation. Okay, that is finding inverses. Now, like I said, that's a tough one, right? Anytime you have multiple x's, it's always going to be a bit more challenging to figure out what the inverse equation is, because you have to do a little bit of like math magic work in there. You can't do anything funky. Stop doing makeup math. I didn't say make it up. I said mathematical magic. All right, you can use your regular math rules, but I saw some people on the quiz doing some made up math stuff. All right, so don't make it up. It has to be real math. All right. But you have to be careful. All right. That's what I'm saying. So that's probably one of the harder examples that you guys will have to kind of work with in this unit anyways. Okay, so next piece, we're moving on, is a way that we can use inverses, or I guess more so how we can use composition of functions to learn about inverses. So basically, if you have a value, all right, so I have this apples and bananas thing, which I know maybe doesn't make a lot of sense, but when I saw it, the picture, it like clicked for me. So I copied it and I saved it and I put it in the notes. But this is what it's saying. So if you have an apple and you put it into your function and it spits out a banana, well, if you take that same banana and you put it into the inverse function, it's going to get you back to the apple. Okay, so function f turns the apple into banana. The inverse function turns the banana back to an apple. That's what this is saying, which I know is kind of funky, but I don't know. Visually, it made sense for me. I don't know. I thought it was kind of a cool visual. If you think it's stupid, that's okay. All right, but basically what this means is that if we take a function and we compose it with its inverse, something nice is going to happen. So if we take function f and we put the inverse function inside, it's going to give us just x every single time. No matter what function you're working with, whether it's a square root function, a rational function, an exponential function, any type of function, if you compose a function with its inverse, it will always simplify to just x. Now, why is this important? Well, two reasons. Number one, you can quickly figure out if two functions are inverses of each other by using this technique. So sometimes, say on your test you're going to take in a few days, if you had to figure out what the inverse was, you wanted to double check your answer, you could just do a composition of the original equation and what you got for the inverse, and if it simplifies down to x, then you know you've done the problem correctly. You've gotten the correct inverse. So we're going to practice, all right? So just using this technique. So here's the question. Determine if the following two functions are inverses of each other. All right, now some of you might be able to look at it and figure out yes or no. Some of you would maybe do the strategy where you take one of them, flip the x and y's, and then see if you get g of x. Like I see a lot of times students do that. The problem is sometimes it's harder to make the inverse equation than it is to just do the composition of the two, because they actually simplify really quickly if they're inverses. All right, so this is kind of another technique for answering this question. So let's just go ahead and do it. It also gives us practice with composition of functions, which is definitely a technique that you guys are going to need for calculus next year. No matter what version of calculus you take, they do a lot with composition of functions, where you put one function inside of another function and then you simplify. That's composition. Okay, so anyways, here we go. If we want to figure it out, let's take function f. Oops, wrong one. All right, so let's do green. I don't know, I haven't used green in a while. Okay, so we're going to take function f and we're going to put g inside. All right, so we're composing g and f. Okay. Now, according to the apples and banana principle up here, if I put g of x inside f of x and it simplifies to x, then these are inverses of each other. So let's see. All right, so I have 3 times, all right, so remember everywhere I have an x in function f, because that's my outer function, I'm going to replace it with g of x, which is x plus 2 over 3. So instead of 3x, I have 3x plus 2 over 3, and then minus 2. Now all I want to do is simplify. So I have 3 divided by 3, which is going to simplify out. That leaves me with x plus 2 right here, and then minus 2 on the outside. Well, plus 2 and minus 2 make 0, so I'm left with x. Guess what? Yay, it works out. That's all I had to do. Check, they're inverses of each other. Now, it doesn't matter which order you go in, so you could do it the other way. All right, so say you wanted to, maybe it looked easier to put f inside of g. Sometimes that happens. So you could also do it the other way. Hold on, let's make this a little bigger. A little bigger. All right, so like I said, you could also do this the other direction. So you could also put f inside of g, and if they're inverses, they will also simplify to just x. Now you don't have to do both ways. You get to pick one, but I'm just saying it doesn't matter which one you choose. All right, so let's do it the other way. So remember, now g is the outside function, so now we're putting f inside of g. So g has x plus 2, so now it's going to become 3x minus 2 plus 2 all over 3. Right? We're just replacing x with whatever f of x was, which was 3x minus 2. So now we simplify. Well, we have a minus 2 and a plus 2. That's going to make 0, so that leaves us with 3x over 3. Well, that simplifies. 3 over 3 is 1, so we're left with just x. Bam! Look at that. See? So fast. So yeah, so I would say yes, of course. They are inverses. Yes, they're inverses. Right? And that's all there is to it. Now, like I said, this is just one of many ways to figure out if functions are inverses of each other. Like I said, you could do it graphically. You could put both of these into your graphing calculator. And like we talked about above, if it's a reflection over the line y equals x, then they're inverses of each other, right? Coordinate points, you're looking for all the points to have flipped their x and y values. So you could do that by looking at the table. You could also just take the function f and then swap the x's and y's and get y by itself to make its inverse, and then compare and contrast with g of x. If it's the same, then obviously they're inverses. But like I said, sometimes it's just easier to do it this way. This was really quick, right? As long as you understand composition, so you just put one function inside the other one and then you simplify. It was like 2 steps for each one, right? And you'll remember, you only have to do one of the two. You don't have to do them both. So on your homework tonight, I have you guys practicing using this technique of compositions to figure out if things are inverses. And I really want you to try using this method. Now, sometimes this is the harder method. Sometimes it's easier. It all depends on the problem. But I really want you guys to practice using that composition technique. Anyways, that is it for this video on inverses. I hope that was cleared up any questions you guys might have had about inverses maybe from last year, or maybe you didn't even know what an inverse was. That's fine. That's what I'm here for. But yeah, that's it. So hope you guys enjoyed, and I will see you in our next video. Bye, guys.